My name is Tiffany Barnes, and I'm teaching this section of CSC 224, which is Discrete Mathematics. It's basically a preparation course for any kind of computer science that you want to do. Basically, we'll be introducing you into all the math concepts that you're going to need in the next 5 or so classes that you need for your certificate. That includes any programming classes that you're going to do, data structures, any numerical methods classes. You're going to use some of the things that we'll learn in here. So I'm going to go through, in a minute, I'll go through exactly what is discrete mathematics. But first, let me let you know a few details about the class. So your textbook is Discrete Mathematics for Computing by Rod Haggerty. They should have this at the bookstore. Also, you can get this used. I checked online. You can get it at bestbookbuys.com. So some teachers have already been using this book, and you can get it used, I think, for about $33. I believe at the bookstore it's about $50 new. So we will be using this book, so you will want to have a copy or at least have a best friend that will let you use it as much as you want. Okay? So I would like for you to read it. It has lots of examples in this book. I've been working with it, over the break, and I think it's going to be a good book for the course. Normally we've been using the old Kenneth Rosen book, which you could use as a reference if you'd like, but we'll be doing all of our homework and examples out of here, except for the ones that I make up for you. There will be a course website up later this week, and it will be available from courses.ncsu.edu, and I will give you the exact address next time. I'm going to give you a handout with some notes next time, and the syllabus will be printed in with that, and all of that will also be available on the website. We'll put any handouts that I give you will also be available. Usually I'll put them in Word and in PDF on the course website. I will have announcements on the website so that if there's any change in when homework is due or something, I'll be letting you know, and I'll also be emailing the class. So I will expect you to check your email outside of class, especially say that, we took a little extra time to cover a topic and you think, oh, I'm not really ready for the homework. Really be sure to check your email then, because I will email you if I decide that you don't have enough material to do your homework, then we will change the due date. We're going to have, before I talk about when homework is due, let me also let you know about our teaching assistant. His name is Andrew Barnes, and he's my brother. And we've been working together to do this course for a few semesters. We just taught CSC 226 last semester, and we had 270 students, so this is a lot less. We're going to be setting some office hours, and we'll be posting those on the website, and I'll let you know later this week exactly when those are going to be. Our offices, we have 2 offices in Daniels, which is on main campus, 131G and 132. Phone numbers are here for both of those offices. So if we're not in one, you can try the other one. Normally during the day, we'll be in one of those 2 offices, either me or Andy. The easiest way to get in touch with me outside of class is to email me. I check email every single day, except for the weekend. I don't always check it on the weekend. So you can email me anytime you have a problem. I'll be happy to write back to you. And my brother also, in general, if you have a question about grades, you should mail my brother, mail your TA. And if you have another question, you can mail either one of us. Because if you email me about a grading question, I'll tell you to talk to Andy. So. Okay, to give you a general idea of the course, we're going to have 10 homework assignments. We're going to have 4 tests and 1 final exam. Sorry about that. I will be assigning exact credit for those by the next class when I give you a syllabus, so I'll have amounts for that. And we're also going to have 3 to 5 computer tutorials for you to take, and those will also count towards your grade. And all of that information will be in the syllabus that I'll hand out to you on Wednesday. Basically, the computer tutorials are online programs that you can take that'll basically go through one of the concepts for the course, and you'll answer some questions, and they're cool little programs. So, and they'll help me with my PhD work, so I would love for you to take them. The final exam will probably be optional, so I will let you know that on Wednesday. Normally that's how I do the class. We have the tests, and you can keep your grade before you take the final, or you can take the final to improve your grade. That's normally how I do the class. Are there questions about that? Just to give you a relative idea, the homework assignments are probably going to count about 1/3 of your grade, and the tests will count about 50% of your grade. And the computer tutorial is about 5%. I'm guessing here. Okay, I'll set them exactly.
Yeah, I was just wondering, how has the performance of this course been on the students you've taught so far?
Has anyone looked at the websites to see the grade distributions? Yes, you want to tell them?
About 20% tend to get A's, 10% tend to get B's, another 20% tend to get C's, and another 10% tend to get D's.
Okay, that's a little different than when I teach this class.
It was like Balik's class.
I teach this class with Dr. Donald Bitzer, so if you look up reviews of this class, if you look under the instructor Donald Bitzer, it'll show you the grade distributions. But in general, we have about 30% A's, and about 30% B's, and about 20% C's, and the rest are below that. So in this class, I'm not trying to put you all against each other and see who does the best, and those people get A's. In general, I want you to understand the concepts that we present, and if you understand 90% of them, you will get an A. If you understand 80% of them, you will get a B. If you understand less of that, your grade will be according to how much of the material I believe that you have an understanding of. I'll encourage you to work together on homework assignments. I don't know how your situation is outside of class. If you know someone else in here, I encourage you to work on homework assignments with other people. And when we schedule the office hours, I will encourage you to come to those as well, because other students can come to campus at that time and you can work together with other students. A lot of this material will be new for a lot of people, especially if you haven't taken any classes for a while. So it'll be good to work with someone else and sort of bounce ideas off of each other.
A question. For our homework, can we do our homework at home in PC, or we must do the homework in the mainframe in the computing system facilities in school?
Your homework will all be on paper. You can write your homework on paper and give it to me in class.
Okay.
So you will not need a computer for any of your homework except for the tutorials. Okay. So because most of the work that we're going to do in this class is mathematics, straight mathematics. So we're not going to be coding. There will not be any programming assignments, although I will use references to coding because that's what you're preparing for. So I'm going to try to frame a lot of examples in terms of when you're going to need to know this for programming or for analyzing code, because that's what a lot of discrete mathematics is. So let me get started talking about that. The word discrete basically means distinct objects. And the reason why we need to talk about distinct objects in computer science is, the reason why we need to talk about distinct objects in computer science is basically any problem that we're going to solve, we need to talk about stuff. And we don't usually want to talk about an infinite number of things, so we want to talk about sets of things. So usually small sets of things, or at least things we can count. Because on a computer, that's all we can solve. You know, we can only store things, sets that we can count, because you can count how much memory you have, and when that's over, that's it. You can't put anything else on there. So in computer science, you're going to often be talking about systems that have discrete numbers of elements. So this course is called Discrete Mathematics because we're going to be studying lots of different kinds of sets and how to do things with them, count size of sets, and that sort of thing. So let me give you a list of topics that we'll go over in this class. First, we're going to do some logic. We have 10 main topics. So we'll do logic and proofs first. Then we'll do logic circuits, which will be quite elementary for you if you have done any circuit design before. But it's still good for you. Okay, let me get my notes so I don't miss anything. This may not be the exact order of how I'm going to do things, but these will be all the topics. Okay, we'll have set theory. And a lot of these won't make any sense to you yet. We're also going to have predicate calculus. Induction. Recursion. Big O notation. Binary relations. Counting. And graph theory. The reason why we start with logic is because that's the basis of all computer science. So if you were to think about how to make a system that would solve problems, first you'd need a way to represent things. And so logic is the very first foundations of representing ideas. And logic basically deals with statements that are either true or false. So when we do logic and proofs, what we're going to be doing is looking at how we represent statements that are either true or false, then how we combine them, and how we can use some rules to derive one true statement from another. When we do logic circuits, that's how we're going to implement our true and false statements and combining them together and figuring out what the output's going to be. Set theory is basically a language for describing sets and manipulating them. So that's going to be important because, like I said, we're going to be studying finite sets of things, so we need to be able to count how big they are, recombine sets, take the union of two sets, that sort of thing. Predicate calculus is logic on larger sets of things. So a statement that's true or false can be true for every single person on the planet, or maybe just one person. And so predicate calculus is going to let us quantify when something is true. Induction is a method of proof where we can use a method that will let us prove something for an infinite size set. So it's easy to prove something for a small set because you can just pick out each element and prove something's true about it. Right? So if you had a bag of marbles and you had to prove all of them were red, you could take each one out and say this one's red, this one's red, this one's red, this one's red. But if you have an infinite set, you can't do that. You don't have enough time to do that, so you need to have a method that will prove that something's true for the entire set. Recursion is a programming method that, how many of you have heard of recursion? Okay, so it's a very important programming method which also lets us do infinite things without having to write infinite lines of code, which is really great. Actually, recursion lets us write very few lines of code and says, do what you did before. So we're going to be looking at that in a mathematical sense. We're really not going to be writing recursive programs, but we're going to think about them that way. Big O notation is the study of how big functions are. And that sounds a lot different than the rest of the things I've been mentioning, but it's very important in coding to be able to tell how fast your code is going to run. And so we use Big O to say approximately how fast a program is going to be. So say that I have 100 inputs, I would, with Big O notation, I would say in terms of that 100, how long is the program going to take? Twice that, take the square of that, take factorial of that, exponent of that, basically to tell me how long the program is going to run, because then I can compare two algorithms. If I can say this one takes approximately n cubed, if I have n inputs, and this one takes n squared, which one would you pick? The n squared. So that's why we have Big O notation, because if you look at like how long a program takes to run and you write an exact, equation for it, it might have lots of, things like x squared plus 5 log x plus 10, and the other one might be 1 million x plus 7 plus a bunch of stuff. We're going to reduce those down to things that are easier to compare for people, and that's why we do Big O. Binary relations is the study of relationships between objects. So one example of a binary relation is less than or equal to. So if I compare two things, it's either like 3 less than 5 is true, but 5 less than 3 is not true. That's one binary relation. We're going to be studying those because those also help us generate study sets. Counting is important because we'll be counting objects in sets. We'll also be able to use counting to figure out how many test cases we might need to generate for a program. So, for example, you might need to know, how many inputs could someone have if you let them type 5 things before you accept their answer. So you might need to know how many possible inputs there are, so you know how many test cases you need to generate to test your code. And graph theory is also a very abstract topic. All of them are. I'm very sorry, but you'll be all right. Graph theory is the study of pictures with dots and lines that connect things, and I just love that because it helps us solve lots of problems like how to build networks. It can be used to represent how cities are connected by roads or airlines or anything, and a lot of times we're going to use graphs to represent problems and then solving the problems. So we'll take a real-world problem and map it onto a graph and then figure out how to solve it with the graph and remap it back into the real world. So it's a lot easier to deal with a picture with dots and lines than it is to deal with a lot more information. So that actually brings me to the basic reason why we have discrete mathematics, and that is because we're basically modeling the real world. So all of these systems that I've mentioned that we're going to be studying in this class are ways of modeling the real world. So basically we're going to be abstracting something that is sort of big and fluffy into something smaller that we can work with. So we'll just go ahead and get started with logic. So we'll start with the definition. So we're going to start with what's called propositional calculus. How many people like calculus? Nobody? Good, because we're not going to do any. Okay? It's called propositional calculus because it's ways of recombining propositions. Okay? So a proposition is a statement that is either true or false. So that's going to be our basic unit for working with a computer. So what would be an example of a proposition? Anybody?
A 1 or a 0.
A 1 or a 0. Is that a statement that's true or false?
All right.
This class begins at 6 o'clock.
This class begins at 6 o'clock. That could be true some days and false other days, right? So that's a good example. This actually introduces one of the problems with English or any language that you might use, which is why we have propositions in the first place. This is sort of ambiguous. This class begins at 6 o'clock. Is that 6 o'clock in the morning? Is it 6 o'clock at night? Is it 6 o'clock Eastern Standard Time? So this is the real reason why we have things like propositions and languages that we work with. So this is ambiguous, but once I say, when someone asks me the question, well, does that mean 6 p.m.? I'm going to say 6 p.m. Eastern Standard Time. Okay, and that's if you're in this section of this course. And then this statement would be either true or false. So this is a proposition. Give me an example of something that's not a proposition.
X equals 3.
X equals 3. Okay, that's not a proposition.
1 less than 5.
Now 1 less than 5 is a proposition. It's either true or false. I can say that's true or that's false. But x equals 3 is not a proposition because I don't know what x is. Okay, so it could be an assignment, but not a proposition. Because some x's might be equal to 3 and some of them might not. So a question is also not a proposition, right? So are you hungry is not a proposition. Are there questions about that? Yes.
I was wondering, I thought, are you hungry could be, you can't be hungry or you're not hungry, yes or no?
The answer is either yes or no or true or false, but the question itself is not a statement that has a true or false value. That's the difference. So if you say, are you hungry true? The statement itself is not true or false. It's just a question. So as I mentioned before, we're going to do predicate calculus a little bit later, and that's going to help us with statements like this. I can make a statement like this into a proposition by saying, I could say, this little symbol right here means there exists, and we'll look at it later, so you don't have to worry about it now. But if I say there exists an x so that x equals 3, that would be a proposition, and it would be true if I was just talking about the real numbers. Okay, so that's a proposition, but the x equals 3 by itself is not one until I give a value to x. You can think about that kind of in the same way as you think about whether your variables have values or not in a program. So when you assign your variables to a value, until you assign a value, you can't say anything about their values. You can't say what they are because you don't even know which operating system you're on or how it sets up your variable. So until you give an assignment to a variable, you don't know what its value is. So basically, we're going to be dealing with things that we do know the value already. Okay, so the next thing we need to know is how we combine these, because they're not very interesting by themselves. It's not very interesting to say the sky is blue, the sky is not blue. Okay, so we want to be able to put things together because then we can build a reasoning system. Okay, so the first thing we need to know is how to say not. So if you want to say something's not true, let me put a marker here. Okay, then I use a symbol that looks like this. So if I wanted to say P is that I am wearing a purple shirt, that's a statement that's either true or false. So P is a proposition, and I've just assigned it to a statement. And then P will be true when the statement is true, and P will be false when the statement is false. So if I wanted to say that I am not wearing a purple shirt in this system, how would I write that?
Not P.
I would write not P, so I would just use my not symbol and write P. So that's equivalent to saying I am not wearing a purple shirt. So when I have a proposition that's either true or false, then, and I'm talking about P here, then I always know that either P is true or not P is true, right? Because I've already said it's either true or false, so either P has to be true or not P has to be true. We're going to be using that a little bit later. Okay, I can also say and. I might want to say that two things are true at the same time, right? So let's just say that Q is, I have a big Q on my shirt. I have a Q on my shirt. Okay, so if I wrote P and Q, this is the symbol for and. It looks like an A without a bar in the middle. If I write that, that means I have a purple shirt on with a Q on it. There's lots of ways to write that in English, what P and Q is. Literally, it would be, I am wearing a purple shirt and I have a Q on my shirt.
If you were to take P and change it to the statement to P equals, excuse me, P equals, am I wearing a purple shirt, then it would not be a proposition. Is that
Right,
correct?
it would not be a proposition. So we actually wouldn't use this language for it, hopefully. So
It wouldn't make any
I'm
sense.
using P's and Q's because that's what people traditionally use in logic. So if you open a logic book, it's going to have P as your first proposition because P is for proposition, and Q is the next letter in the alphabet, so that's what they use that for. But P's don't have to come before Q's, and you could use other letters also. Okay? I always say that in this class that we have to speak two languages. We have to speak English and we have to speak math. So every time I teach you something, I want you to be able to talk about it in mathematical terms and write it down in mathematical terms, which I'm teaching you the symbols that we're going to use for logic. And I also want you to be able to tell your grandmother what you just wrote. Okay? Your grandmother or some other person that doesn't know math. So if your grandmother's a logic professor, then you have to tell someone else. Okay? So I want you to be able to tell someone else what you're doing in regular English language, because that shows to me that you really understand it and you're not just writing what I told you to write. So the next operator we're going to use, or the next connective, these are called connectives. Let me write that down. So we're talking about connectives because these are going to be used to make compound statements. So we're using P, using the AND to connect P and Q. They're called connectives.
It's not a connective.
No, it's not a connective. It just is a symbol. So connectives are things like and or, and we're going to do implies in a second. So or is the next one. And or are the basic building blocks for all the other connectives that we might talk about. Because you can build any of the other ones using and combinations of ands and ors. And nots. You have to have nots also. Okay, so or is written as the upside down and, which is quite confusing for a lot of people. But you can remember A is for and it looks like an A without the bar, and or is the other way. Also, if you already know any set theory, this is like union, and the and is like intersection. So, also, you can also think about this as plus, and we're going to do that later. And you can think of and as times. So let me put this back up and put a little times next to that. Okay, and also you can think of it as intersection.
So if you wanted to write not P and not Q on the other one, you just do the not sign P and not sign Q.
Right, so that's right. If I wanted to write not P and not Q, that's how I'd write it. So that is not P and not Q. That's how I read that also. Okay, so or is written like a V. So if I want to say P or Q, I write P or Q. Now we have a question because and is pretty unambiguous. When is an and statement true? So when would P and Q be true?
If B is true, Q is
Both
true.
are true.
When both P are true, P and Q are both true. So let's make a diagram of when they're true. Okay? So first of all, we're going to make a diagram for when P is true. So it either has a true value or it's false. So sometimes it's true and sometimes it's false. I don't know because I don't know what P is. So this is where we're getting a little more abstract, right? So we're going to make a table and we don't care what P is anymore. We're just going to talk about whether it's true or false. This is what a computer does. It doesn't know that you said P means that I have a purple shirt on or I'm wearing a purple hat or anything. It doesn't know that. It just knows what your values are that you told it. So we're going to make things called truth tables. So this is called a truth table. Now, why do you think we might want to do this?
Probably gets pretty confusing when you do more ands and ors together.
Right, when we start combining propositions, it gets more and more confusing. The more we have, the more confusing it is to know when it's going to be true or not, when the statement that we're doing is going to be true or not. So we want to make a table so we can make sure we're covering all the bases, like we know exactly when something's going to be true and when it's not going to be true. That's very important because when you're writing a program, you want to know, when am I going to go into this if loop, right? When am I not going to go into it? So that's very important to know. So if you can make a truth table, then you can always find out. You can always figure it out and make sure that you wrote the right conditions to get into your if loop. So I'm going to go ahead, the book doesn't do this very early, but I'm going to go ahead and tell you that in computer science we use 1 for true and we use 0 for false. Okay, and then I'm going to reverse the order of this. So if you open a logic book, they're always going to put the truths first, and then they're going to do falses. But we're going to go ahead and start out doing falses first. So I wrote it true, false, because that's how you do logic. But then when you start using zeros and ones, you always start with the zeros. Because we're going to count. We're going to count on our truth table because then we can check and make sure we have enough cases covered. So I'll show you an example of that. So if I have two variables, let's say I have P and Q. Okay? What are all the ways that we could have P and Q? Like if I have to cover all the cases, like how many different possible combinations are there? We're going to start with counting. We're not on the counting section yet, but we have to start with it. There are 4. Why are there 4?
P first.
Because each one has got 2 cases.
Because each one has 2 cases. So P can be true or false, and Q can be true or false, and then I have to do all the combinations, right? So I have to combine the true for P with the true and the false for Q, and the false for P with the true and the false for Q. So we'll go ahead and write the truth table the way that we're always going to write it. Make a table, make a column for P, make a column for Q, and then we're going to make a column for the compound statement of P and Q. So first we're going to look at the false values. As I said before, we're going to look at the false values for P. And there are 2 of them because I have to combine them with the false and true values for Q. And then I'm going to have 2 true cases for P with the false and true values for Q. So in the first 2 cases, P is false, and in the second 2 cases, P is true. And then I have to combine, with those values for P, I have to combine all the possible values for Q. So just let's say, just be a little bit more abstract for a second, if Q had 3 values, how many rows would I have in this table?
6.
I would have 6, because it would be like having 0, 0, 0, and I'd have to have 0, 1, 2, and then I'd have to have 1, 1, 1, and 0, 1, 2. We're going to do some examples like that later when we're talking about sets. But right now we're going to be talking about propositions. So in this case, we're going to have 4. So when did we say P and Q was true?
When both are true.
When both P is true and Q is true. And which row in the table is that if I number them from 1 to 4?
Fourth.
The 4th one. So that's true in that case, and it's false at all other times, right?
Yep.
So here's our truth table for P and Q. This is the most fundamental truth table in all of logic. So this is a very good one to know. It's also cool because it only has 1 1 in it. That means I know if this statement is true, I know a lot of stuff. I know P is true and Q is true, right? Or is a totally different situation, right? If I know the or is true, that doesn't tell me much about the individual variables, right? So let's look at a truth table for that too. And if you notice, I'm going to make the truth tables the same always. I'm going to put 0, 0, 0, 1, 1, 0, 1, 1. And this is typical in engineering. That's why I always do it this way. I start out with this order. And if you also, how many people can count in binary? If you look, this is counting in binary. I start with 0. 0, 0 represents 0 in binary. 0, 1 represents 1 in binary. 1, 0 represents 2, and 1, 1 represents 3. And we're going to talk some more about that later. But this is the one way that you can check that your truth table has all the values, because I know that this truth table should have 4 values, because I have 2 variables with 2 values each. So it should be 2 times 2 rows in my truth table, and then I can count in binary from 0 up to the number of rows minus 1. So this one I can count 0 up to 3, 0, 1, 2, 3, and I know I have all of my rows. So we always want to make sure that everything we write down is completely true. We always want to be able to double check it. And that's why we write our truth tables this way. Okay, so let's make a truth table for or. My pen is running out, so I'll get another one. So again, we start with a column for P, a column for Q, and we make one for the or. Remember that or looks like a V. So I put all the false values for P, the true values for P, and then I alternate 0, 1, 0, 1 for Q. We're going to make larger truth tables in a minute, so you'll see how we'll do 3. Okay, so when is P or Q true?
Either of them is true.
When either one of them is true, or
They're both false.
when both of them are true, right? This is the difference between logic and English. Okay, we're going to talk about that for just a second. So here's our truth table for or. It's true as long as both of them aren't false. Okay, so in English, when I say I'm going to go to the store or I'm going to go to the movies, a lot of times people assume that that means you're not going to do both, right? But in logic, it always means it can always be true if both of them are true. So that's the difference between English and logic for the case of or, because sometimes or means exclusive or, and we're going to do a truth table for that in a second. Another operator called exclusive or, but or means either or both. So either P or Q or both. So I'm going to write that down. Either P or Q or both. And as I said with the and truth table, we knew a lot when we knew P and Q was true. We knew that P was true and that Q was true. But in this case, we don't know which one is true or even if both of them are true. So it might be the case. All we know is that it's not the case that both of them are false. But or is extremely useful too, though. So these are the two basic building blocks. You can make any circuit. You can build your entire computer using just these two truth tables. Isn't that cool? I think it's pretty cool. And we're not going to do that in this class, but if you take 312, or that's what it used to be called, Computer Organization and Logic, you'll do that. So I mentioned an operator called exclusive or, which we write XOR. And this is one that we often use in English, exclusive or. We often mean one or the other, but not both. So if I write, here's the operator, it's a plus with a circle around it. That means either P or Q, but not both. So we'll make another truth table. So in this case, we're going to have a true value for the exclusive or when either P is true or Q is true, but it's going to be false when both of them are true. So tell me which rows are going to have true values for P exclusive or Q.
2 and 3.
Rows 2 and 3 will have trues, and the other ones will be false. Are there any questions about this? In general, we're mostly going to be using ands and ors in this class, but I do want you to know what exclusive or is. We have one other operator that's really, really important, and actually it's the one we're going to use the most. And that's called implies. We write it as an arrow from P to Q, and it's written, or it's read, if P, then Q. You can also write it, or say it, P implies Q. And this is the most important operator that we'll be using in logic. It's very important to have an understanding of the others, but this one is going to help us reason the most. Because it's not often true that and statements are always true or that or statements are always true. But an if-then statement tells you things about causation, right? Tells you that if one thing happens, then another thing is going to happen. And we want to do that a lot in programming, right? Say if a value is less than 0, we want to kick the person out of the program because they were supposed to enter a positive value, okay? Or that sort of thing. So we want to use conditions all the time. And there's my pen. Sorry. Okay, so let's figure out what the truth table for this is. And I want you to think about P implies Q as a contract, because this is the one that's most confusing about when it's true, like telling when it's going to be true. So maybe before we make the truth table, let's talk about a statement. Okay? I like to use examples of little kids because all of us were kids and we remember being with our parents. Okay? So let's suppose your mother made you this promise. If you are good, then you can have candy. Okay? So this is a statement, P implies Q. P equals you are good, and Q equals you can have candy. Okay? So now let's figure out when your mother lied to you is what this table is about. It's not about whether you get candy or not. Okay? That's what's tricky about this table. Okay? So when did your mother lie?
3.
3.
Right, it'll be the third row, but let's talk about it in English. She lies if what? If you're good and you don't get any candy. That's when you start screaming, right? If you're a temperamental little kid. You're like, I was good, I did everything you told me to, and you're not giving me any candy. And then she's really going to have to do some real explaining, right? Okay. But the rest of the time, suppose that you're bad. Can you complain if you didn't get any candy? No. You might complain, you might say, I was good, and she could go, right. How about when you threw your little sister, out of her bed? That's not good, right? So your mom can argue back at you that she still kept her promise. So we're going to talk about when we've kept the promise. Okay, so this is being good, and this is getting candy. So if you're not good, she didn't lie, right? So this statement is true. So if you're not good, either one of these cases, if you get candy, you're still happy, right? She might give you candy anyway to make you be quiet. But she didn't lie to you. If you weren't good, it was still true that if you are good, you're going to get candy, right? In this case, if you're good and you don't get candy, then her promise is broken, right? So this statement is false. So this is where you want to think about. You want to think about the promise being broken. And in this case, if you're good and you get candy, then she kept her promise, and this statement is true.
Why isn't number 2 false when you get the candy?
Number 2 is not false because her promise isn't broken. So this statement is about whether the promise is broken or not. So let me make a really extreme example that I got from another logic professor. He told me this example for teaching this. He says, and this is an old example, okay? So pretend that we have Michael Jordan, okay? And he was playing for the Bulls, playing basketball. I don't know who he's playing for now. But back when he was playing for the Bulls, they promised him, they made a contract that said if they win their next game, Michael Jordan's going to get $1 million. So you can think about P implies Q being the contract itself, and when the contract is broken, and when can Michael Jordan sue. Okay? So if they go ahead and make him a check out for $1 million, is Michael Jordan going to sue them? No. So both of these are all right. If he gets his $1 million, so let's put down here, we'll talk about winning down here and getting the money on this one. Okay? So if he gets his $1 million, he's not going to sue them. He can't sue them, whether they win or lose. Right? So even if they lose and he gets his $1 million, the contract still holds. Because they said, if you win, we'll give you $1 million. If they give it to him anyway, he's not going to complain. If they win and he doesn't get his money, that's when he sues. That's where we have a 0 because the contract is broken. If they win and he gets his money, he can't sue because they've done what they said they were going to do in the contract. So this is how you hope that your programs will work. If you write an if-then statement, if the if is satisfied, the then will happen. Okay? Sometimes the then might happen anyway. So another example I like to use is, if it rains, I'm going to get wet. Right? That statement can be true even if I get wet and it didn't rain. Right? Someone could pour a bucket of water on me and I could be wet, but the statement would still be true that I would still get wet if it rained. So I'm just talking about whether the statement is true or not, and that's why this is the trickiest truth table. Because a lot of times when we think about if then, our brain goes ahead and says, did it happen or not? Right? Instead, we want to talk about the truth value of the statement. So it's like we want to think about it like a contract. Did it have, was the contract broken or not? So that's how I want you to think about the implication. Okay?
So anytime that you get Q, pretty much you can say that P implies Q is always true.
Excellent. That was the next thing I wanted to do. Okay, so this, how many ones do we have in this truth table?
2.
How many rows have true values? 3 of them, right? And an OR has 3 truth values, so we can actually make an OR out of this. Okay, but we have to have some nots because it's not exactly like the OR statement, right? Because OR has a 0 at the top and 3 ones after it. So what Maria just said was that any time that Q is true, the statement's going to be true. So what do you think I might OR with this and get the same truth table? So we're going to get ones where there's a Q. So Q is true in rows 2 and 4, so we'll get ones there. Let's make a line here. And we know we have a 1 here, right? So what's true in this case? P is false,
Not P.
right? So if I write not P up here, hopefully that will give me the same thing. So let's check it out, okay? So we need to have a 1 over here. Whenever P is false gives me a 1 in both of these rows. And we need to have a 1 over here whenever Q is true, gives me a 1 in both of these rows. And we don't have 1s anywhere else, so we get a 0 here. And you can see that these 2 columns are the same. P implies Q is the same, is logically equivalent to not P or Q. So like I said, we can build any other compound statement out of ands and ors. This one is equivalent to an or statement. And a lot of times when I'm looking at implications, I'll think of them this way. Either P is false or Q is true. So order matters on this one. If I say Q implies P, that's going to be equivalent to what?
Not
Q or P.
Okay, let me write it down so everybody knows what I'm talking about. Okay. If I say Q implies P, that order is different than this, right?
So it'd be not Q.
Yes.
So if I use the rule I just derived, this one we said was not P or Q. So what do you think this one is?
Not Q.
Q or
Not Q.
This one is not Q or P. So the order matters. The thing that comes first, the variable that comes first, is called the hypothesis. And the second one is called the conclusion. So they have separate names because it matters which one is which. So when I change an implication into an OR, I have to negate the first variable and change the OR into an implication and leave the conclusion as it is. So either the hypothesis is false or the conclusion is true in order to make an implication true. Okay? So we're going to use a symbol for this to tell that these are the same. And it's called logical implication. So this symbol is a very important one that we're going to use. Sorry, it's called logical equivalence. Logical equivalence. So it's just like an equal sign, except we're talking about true false values, and that's why it doesn't look the same as an equal sign. How many people have seen their math professors use something like this? Math teachers use this all the time, or else they use this one. Right? This one's called logical implication. Logical equivalence is just like we can do substitution when we see logical equivalence. So anytime I see P implies Q, since I know that's the same as not P or Q, anytime I see P implies Q, I can replace it with not P or Q because I know that they're logically the same thing. Logical implication is a little bit different. Okay? So logical implication means that I have an implication that is always true. So we'll do an example of that. First, I'll do a truth table for logical equivalence, because we can do proofs of things being equivalent. So we had this truth table before. Where we had two statements, and we saw that they were logically equivalent because they had the same truth table. So what I can do is I can make a column for logical equivalence. And this basically is the same as the symbol. This is called equivalence. This means that P and Q have the same value. So if I have P is equivalent to Q, then they have to have the same value. If it has two lines in the middle, then that means I have to have all ones in the truth table for that. Okay, so I have to check it out. So these two have to be the same because I'm comparing. A lot of times when I make a truth table, I'm going to label the columns and then I'm going to compare them. So this one is going to be a comparison of column 1 and column 2, P implies Q compared with not P or Q. Okay, and so logical equivalence is going to be true when they have both values are the same. So 1 is the same as 1 will give me a 1 in this column. 0 is the same as 0 will give me a 1 in this column. And 1 is the same as 1 is going to give me that column. So this is a proof, this is a logic truth table proof for the statement that P implies Q is logically equivalent to not P or Q. So this is one way to do a proof. You can imagine that if we had lots of variables and lots of statements to combine, that we wouldn't want to make a truth table to do a proof. And that's why next time we're going to do some logic proofs. So let me just mention what this symbol is, because I didn't. So when I have P is the same as Q, so you can read this a lot of different ways. P is the same as Q is one way to read it. P if and only if Q is another way to read it. And that's sometimes written IFF, just so you know. You'll see that in math a lot, IFF. Okay, P if and only if Q. In any other way you can say they're equal is another way to write it. Or you can also write P is equivalent to Q. So this operator is called equivalence. And it is logically equivalent. This is true if and only if, but always, P implies Q and Q implies P. So we're going to do a little truth table proof of this. Okay? So that's why it's a double arrow, because the arrow goes from P to Q and the arrow goes from Q to P, so it makes a double arrow. So if I want to do a truth table proof of this, I'll make a column for P and a column for Q and then a column for each one of these statements. Okay, so let's do that. So we'll make a column for P, one for Q, one for P is equivalent to Q, one for the logical equivalence, one for P implies Q, and one for Q implies P. We know we have 4 rows, so I'm going to go ahead and do those since we have a nice big table here. Okay, and the goal of this, when I do a truth table proof, the goal is to have all ones in this column. So this one's going to be. So basically when I do this, I'm going to be comparing this column with this column, this and right here, because I'm going to be anding those two values on the right-hand side. So I'm going to say the left-hand side's equivalent to the right-hand side. Okay, so let's fill out the values for P, or 0011, 0101 for Q. If you go down the column, P is equivalent to Q whenever P and Q have the same value. So P and Q are both false in the first row, so this is going to be true. In the second row, they have opposite values, so it's false. In the third row, they have opposite values, so it's false. And in the last row, they have the same values, so it's true. And this is exactly the opposite as exclusive OR, right? Because exclusive OR was 0, 1, 1, 0 down the column, and this is the opposite. Because the first row here is P is false and Q is false, and the last row is P is true and Q is true. They have the same value. Okay, so P implies Q was 1, 1, 0, 1, right? It was true whenever P was false and whenever Q was true. So in the last one, we have to figure out what Q implies P is. So this one's going to be true whenever Q is false, which will be row 1 and row 3, and also whenever P is true. So it would also be true in the last case, and it's false otherwise. Okay, I did that quickly, but you should be able to go home and try that yourself. Okay, using the definition. Okay, so if I AND these together, so if I AND column 1 and column 2, P implies Q ANDed with Q implies P, then I'll get 1 and 1 gives me a 1. If I AND a 1 and a 0, what do I get?
0.
0. If I AND a 0 and a 1, I get a 0. If I AND a 1 and a 1,
1.
I get 1. Okay, so if I'm going to compare these two columns, then I can already see that they're the same, right? Because each row has the same value, so I'm going to put a 1 in all the rows where they have the same value. When I have all 1s under the logical equivalence, that is a proof that those two statements, the left-hand side is equivalent to the right-hand side. That's a proof.
Assuming that you've picked the total possibility of all the answers. The total
Right. As
population
long as my
of the
truth
answers.
table is full, if I have all the rows that I should have, then I have a proof. So that's another reason for knowing how many rows you're supposed to have and being able to count all the cases. Okay. So let me just review what we did today. I'll just make a list. Okay? So you know what you need to remember. Okay? We talked about a proposition. This is a true or false statement. Then we said that true was a 1 and a 0, so when we make a truth table, we're going to use 1s and 0s. Okay, then we talked about ways to negate propositions, so we talked about negation, which was the not sign. So we used little letters for propositions like P and Q. So negation would be not P. We talked about AND, which is also called conjunction. And the symbol for that was like a little hat on the keyboard. Looks like a hat or an A without a bar in it. So that's AND. We talked about OR, which is called disjunction. And this is all in your book also. That looks like a V. The symbol for that looks like a V. And that's an OR. We talked about implies, or implication is implication. And that's an arrow from the hypothesis to the conclusion. We talked about if and only if, which is a double arrow, which is also called equivalence. And then we also did exclusive OR, which was written as a plus with a circle around it. We made truth tables for all of these. And we also did some truth table proofs. With logical equivalence. In our next class, we're going to be doing, I'll review this just a little bit. I'll go over implication again because we're going to talk about some ways to do logical implications, which I will tell you what that is next time, because we'll do some proofs of logical implications. and we're going to be deriving some rules that will help us in logic. So for example, if you want to think about it a little bit this week, then, for example, if I tell you if it rains, I'm going to get wet, and I tell you it rained, what do you know? You know that I got wet. So we're going to be talking about doing proofs that use rules like that. So we're going to derive rules like that, and then we're going to be able to write them without making these long truth tables. Because the more variables you have, the more rows you have to have, and the more of a pain it is to keep track of where all the zeros and ones go. Okay? So next time I'll be bringing your syllabus, and so you'll know exactly when the homeworks are going to be due, and all the handouts that I give you will also be posted online.